We are diving into emergent temporal abstractions in autoregressive models enable hierarchical reinforcement learning. This is a fascinating work from Google's Paradigms of Intelligence team. It really shows us how we might finally make reinforcement learning efficient for these really complex tasks by just leveraging what these massive foundation models have already learned. So for the quick summary, the big challenge they were up against is that standard RL fine-tuning of large autoregressive models is it's wildly inefficient for sparse reward environments. And why is that? It's because the exploration is limited to generating actions one token at a time. It makes success almost a statistical impossibility on these really hard tasks.
Exactly. And the profound discovery here, really the core of the paper, is that the internal activations, you could call them the deep thoughts of a frozen pre-trained model, already contain these temporally abstract action representations. These are the reusable subroutines like go to the kitchen or open the door that the model just learned implicitly, all on its own during pre-training.
And their solution, which they call internal RL, is just brilliant. They introduce a separate metacontroller that acts directly inside this latent space of the frozen base model. This metacontroller learns, and this is key, completely without supervision, to generate these long-horizon abstract actions. And crucially, it also figures out when they should terminate, using something called a dynamic switching unit.
Right, and the outcome is really a paradigm shift. This internal RL operates on a radically contracted timescale. It effectively shrinks this astronomical search space, which enables efficient, high success rates on complex, hierarchically structured tasks. We're talking about things like navigating a legged robot through a maze tasks where traditional low-level RL fine-tuning, it just can't find a solution at all. This is a massive leap in sample efficiency.
Okay, so let's really unpack this. We've been living in this age of fine-tuning large sequence models, transformers or the newer SSMs with reinforcement learning. This is how we get models to follow instructions or optimize for certain metrics.
Precisely. And that initial large-scale pre-training, it acts as this incredibly powerful form of imitation learning. So even though the original data might just be these observation action trajectories without any explicit reward signals, the model develops these latent variable inference capabilities. It learns to infer context, intent, goals, which is really what gives it that powerful in-context learning ability we see.
But the architecture itself creates this Achilles heel when you move to genuinely complex environments, especially those with sparse rewards. So say you're training a robot and the only reward it gets is for successfully finishing a 10-step sequence of subtasks. If the model is generating actions one token at a time, or maybe one joint torque command at a time, every single step in that chain has to be correct.
That's the brutal inefficiency right there. If you need 100 correct low-level actions just to get that one distant reward signal, the probability of exploring a successful path randomly is minuscule. Imagine trying to drive a car from New York to San Francisco by only planning the next 1 millimeter rotation of the steering wheel. That's really what token-level exploration feels like for these models.
Right. And that inefficiency, that's the core motivation behind hierarchical RL, or HRL. HRL is designed to discover and use these temporally abstract actions or options that run for extended periods. So instead of planning those millimeters, you're now planning in terms of, drive to Chicago and then drive to Denver.
And that higher level of planning, operating on an abstract timeline, it dramatically reduces the size of the search space. And just as importantly, it simplifies the credit assignment problem. You don't have to figure out which of the million tiny actions led to success. You just have to figure out if drive to Chicago was the right high-level choice to make.
And historically, finding those good subroutines, especially with deep RL, has been notoriously difficult. A lot of methods end up converging to options that aren't actually meaningful or, temporally consistent.
Which is exactly why this paper's core hypothesis is so elegant. They essentially say, stop trying to learn the subroutines from scratch during the RL phase. If these autoregressive models are already performing latent variable inference, if they are internally predicting future states and inferring goals, they must have implicitly learned these useful temporal abstractions inside their internal activations, specifically in the residual stream.
Let's drill down on that. So the residual stream, that data highway running between the layers of the transformer, is basically the model's internal working memory, its thought process, so to speak. And the theory is that the high-level plan is living right there.
Exactly. So the first massive step was just validation. If the abstract plan is in the stream, can we read it? And more importantly, can we control it?
Okay, so to test this, they used two pretty complex hierarchical environments. A discrete grid world pinpad task and the continuous MuJoCo ant pin pad, which involves a four-legged robot.
And both of these tasks require strong compositional generalization. The agent has to visit a sequence of subgoals, these are colored locations, in a specific order. And the critical detail here, which you have to remember, is that the base sequence models were only pre-trained on passive observation action sequences. There were 0 explicit rewards, 0 explicit goal labels, and 0 subgoal markers in that entire pre-training data set.
So nobody ever told the model what a subgoal even was.
Yeah.
But then they applied mechanistic interpretability. What did they find?
They used linear probing. You can think of this as training a very simple single-layer classifier to just peek at the model's working memory, the residual stream activation at any given moment, and try to guess the true underlying subgoal the agent was implicitly pursuing.
And the results were pretty decisive, right?
Absolutely. The linear classifier could successfully decode the abstract subgoal from the latent space. And crucially, the decoding success rate increased as they moved deeper into the network, peaking near the final embedding. This confirmed that the abstract information, the plan, was being synthesized and robustly represented within the network's layers.
Okay, so representation is one thing, but the real breakthrough is controllability. Just knowing the model thinks about a goal doesn't mean you can force it to, change its mind.
Right, and that's where the causal intervention experiments came in. They leveraged ideas similar to LoRa fine-tuning. They introduced a simple, low-rank linear controller, they call it Unsupervised, that modifies the activations right in the middle of a transformer block. It directly injects a signal into that residual stream.
And for this supervised test, they used the ground truth. They manually selected the correct controller, $1, that corresponded to the actual subgoal the agent was supposed to be achieving next. They were kind of acting as the benevolent human supervisor, just for a moment.
And it worked. By activating the correct controller, they proved that the model could be steered. The controlled models achieved high success rates on novel tasks, including those requiring compositional generalization. So combining previously learned subgoals in sequences the model had never even encountered during its passive pre-training.
This validation step basically proved the core theory. Abstract intentions are linearly decodable, and more importantly, they are linearly controllable.
But wait, let's drill down on a fascinating detail here. The best performance came when they inserted this controller not at the beginning or the end, but near the middle layer of the pre-trained model. Why do you think that matters so much?
My take is that it's all about the flow of computation. The early layers are probably focused on parsing the raw input, turning observations into features. The very late layers are focused on the final output prediction, the raw action token. The middle layers, then, must be that sweet spot where the high-level plan, the abstract subgoal, is fully formed and is being translated into the low-level motor commands for the next, say, 100 steps. Injecting control there lets you hijack the plan right before it executes.
That aligns perfectly with what they found. And it resonates with a lot of other work showing the middle layers are often the most effective for transfer learning. It means the model's internal planning cascade is fully formed right there in the middle.
Okay, so we have a clear conclusion from phase 1. The model has these reusable abstract actions stored inside, and we can control them if a human tells us what the goal is. But now we hit the real engineering challenge. You can't rely on human ground truth labels for subgoals in a real-world RL setting. So how do they get rid of the human helping hand and enable autonomous discovery?
This is the shift to the unsupervised metacontroller. The key idea is to freeze the base model's parameters, theta, and only train a new component, the metacontroller, first. This metacontroller is a generative, stochastic, recurrent network that learns to output the parameters UTOC for that linear controller we just talked about. It's essentially a hyper-network learning to generate the steering signal.
And the metacontroller has two incredibly clever architectural elements to make this unsupervised learning work. The first is its ability to peek into the future during its own training.
Right, the future conditioned encoder. So during the self-supervised training phase, the metacontroller is allowed to access an embedding of the entire activation sequence from start to finish. This is non-causal access, and it's critical.
Why is it so critical?
Because a subgoal is only really confirmed or, conclusive once the entire sequence of actions needed to achieve it has actually unfolded.
I see. So if the model successfully navigates to a red block, the metacontroller can look back at the entire trajectory and retrospectively label the segment of activations that occurred between the last block and the red one as, okay, that abstract subroutine was go to the red block. It's teaching itself what its own abstract thoughts mean in retrospect.
Exactly. It's creating its own internal labels for its high-level thoughts. And the second key element is the mechanism for temporal abstraction during execution, the dynamic switching unit.
This is the secret sauce for efficiency. It's a recurrent unit that outputs a gate, they call it $, which is a continuous value between 0 and 1.
And that gate determines whether the current abstract action code should be maintained or if a new one should be sampled and activated. Think of it like the system dynamically generating a macro key that runs until the internal system decides that task segment is complete.
So if batat is near 0, the model just keeps the current abstract plan. If a tat spikes up to 1, it decides the current sub-goal is finished, or maybe failed, and it samples a new abstract goal. It determines the termination condition implicitly, just based on the latent context.
And they train this with a standard self-supervised objective for next action prediction, but with a critical KL divergence regularizer applied to those latent codes, the 0 codes. And this regularizer is what forces the abstract codes to be meaningful, compact samples from a standard normal prior.
And the analysis confirmed that this self-supervised setup works brilliantly. The learned switching gate, it naturally converged to this sparse, quasi-binary behavior. It accurately recovered the exact moments the ground truth sub-goal shifted, achieving perfect temporal segmentation without being explicitly told to be sparse or when to switch.
And we have to emphasize one crucial finding they highlighted with their rate distortion analysis. This confirmed the conceptual victory of freezing the base model weights.
Why was freezing so essential?
Well, when they tried to co-train the base model weights, theta alongside the new Metacontroller, they did required abstract structure just, it immediately vanished. The model converged to a degenerate solution, often just one single switch at the very beginning of the sequence. By freezing the base model, you are relying on the powerful, goal-aligned structure that billions of parameters have already learned during pre-training.
It confirms that the base model isn't just some dumb feature extractor. It's a reservoir of sophisticated, usable temporal structure.
That's it. That two-step process, massive SSL pre-training, followed by frozen weight control, is the architectural key that unlocks efficient HRL. Which brings us to the final payoff, internal RL.
And we have to set the stage here by reminding everyone how brutally the baselines failed. Standard policy gradient fine-tuning in the raw action space just failed completely on these sparse-reward compositional tasks.
It's just a matter of probability. The chance of generating a successful low-level trajectory on that MuJoCo ant task was found to be on the order of 1 in a million. So even giving the models millions of training episodes wasn't enough to generate a usable signal. The brute force approach just breaks.
It doesn't work.
No.
Yeah.
And prior HRL methods also failed. So internal RL, it's not just an improvement, it's the only method that works here. It's a complete paradigm shift, defining a new RL environment where the frozen, pre-trained autoregressive model is part of the environment itself.
So what does the agent now see and do in this new world?
The RL policy no longer observes raw pixels and outputs raw torques. The observations for the RL agent are the internal residual stream activations, ETL, and the actions are the high-level abstract controller codes, ZTL, generated by a new causal policy.
And this is where the time compression gets applied. They take that learned switch gate, byte of my $, and they binarize it during the RL execution phase.
The result is dramatic. Until the Metacontroller emits a switch signal, so until batat spikes, the same abstract action code runs the base model, controlling the robot for potentially hundreds of low-level time steps. This contracts the planning horizon immensely.
And the final metric just proves the point. Internal RL rapidly achieves high success rates where all traditional methods failed, even with massive training budgets.
And they ran a crucial ablation study on this. They disabled the time compression feature, forcing a switch at every single time step. That baseline failed too. This confirms that the success isn't just about using a compact latent space, so levelers.
It's the learned dynamic temporal compression. That's the essential ingredient.
Exactly. Analytically, the advantage is crystal clear. By operating in this low-dimensional, abstract latent space on a contracted timescale, internal RL dramatically reduces the variance of the policy gradient estimator. It's a perfect mathematical lever for efficient credit assignment in these sparse reward settings.
So if we look at the bigger picture here, this finding adds some really powerful positive evidence to the ongoing debate about what these autoregressive models are truly learning. The fact that they develop consistent, temporally abstract, and controllable plans internally. It pushes back hard against that argument that they are merely stochastic parrots, just regurgitating data patterns. They are modeling hierarchical intention.
It also provides a beautiful, concrete neural architecture realization of a decades-old theoretical structure proposed by Jürgen Spitthuber, the alternating wake-sleep loop.
Right. History compression via self-supervised learning. Then the controller uses those internal representations for RL to generate new, better experiences. Pre-train the compressor, then reinforce the controller in the compressed latent space. It's so elegant. This innovation cuts the search space by dynamically compressing time in tasks, from grid navigation to complex motor control. So let's think about where this goes next. We're seeing enormous interest in high-level LLM reasoning methods, things like chain of thought, which are basically explicit sequences of abstract reasoning steps.
This really raises an important question for you, the listener. If internal RL is this effective at optimizing abstract actions in a robot's motor control, could applying this exact dynamic time compression approach revolutionize how we apply RL to optimize high-level LLM reasoning processes? If the LLM has already learned abstract steps of reasoning during its pre-training, could internal RL be the key to stitching those steps together efficiently under sparse rewards, like getting a single high-quality answer on a complex multi-step query? Could this lead to far more efficient knowledge acquisition in open-ended language domains?
Using internal RL to reinforce the abstract thoughts, not just the output token. That's a phenomenal target for future research.